Okay, let's talk about electricity. How do charges interact and what happens when charges actually move? So, first thing we need to talk about is the electric force. That is one of the four fundamental forces. Right here is a review if you need to go over what those were again. And this is something that can either attract or repel. So with an electric force, it can pull something closer or it can push something apart. And you have to think about the parts of the atom when you get down to this. Protons are the positively charged parts found in the nucleus. Electrons are negatively charged and they orbit, more or less, the nucleus. And the neutrons are the neutral ones, also found in the nucleus. So there we can see the protons and neutrons in the middle and electrons around the outside there. Protons positive, electrons negative. In neutrons, no charge. Like the old joke, a neutron walks into a bar, orders a drink. When he's done, he says, "Hey, bartender, how much?" And the bartender says, "For you, neutron, no charge." Okay, I'll stop. With the electric charge, you have to go to a new law that we've talked about, the law of conservation of charge. We've talked about law of conservation of energy. This one basically says the same idea. You can't create a charge and you can't destroy a charge. All you can do is separate it. We'll do a lab in class that will demonstrate that. Things that are like charges will repel. So two positives or two negatives are going to push apart. But opposite charges will attract. So if you hang these things here, these are called pith balls and they can have different charge. If you have two positive ones, they're going to push apart. If you have two negative ones, they're also going to push apart. You know, they're essentially fighting gravity. They don't want to be near each other. But if they're opposites, they're actually going to attract to one another. So like repels, opposites attract. Here you can see on a dog, if you've ever gotten something like, all electrified and all charged up there, those hairs are standing on end, not because they want to, but because they're all the same charge. They're all negatively charged. You essentially rubbed it so that, you separated the charge. And when they're all the same charge, they want to get away from each other. They don't want to have anything to do with one another. And the way you do that is they separate. They stand up. Here's another one you can see. Someone looks like they rubbed their dog with a Snuggie and it looks like, all puffed up like that. Those hairs are all the same charge, so they want to get away from each other. All right. Electric current is what happens when you have electrons flowing, usually through a wire. I want you to draw this diagram in your notes. So here we have the battery. Here's the positive side, which means this is the negative side. An electron is leaving there, going through and lighting up that light and then returning to the battery. So the flow in this case here is in a clockwise direction. That forms an electric current. We have two types of current. This one right here is called DC or direct current, where the flow only goes in one direction. A battery is a perfect example of something that is DC or direct current. Alternating current is different. That's what you're going to get actually, coming out of the outlets in your house. The flow of the electric current is constantly switching directions. We would say that it alternates its current. So in direct current, it comes out, it goes in one straight way that way. Alternating, it switches back and forth, back and forth, back and forth, so that in the end, what you're left with is it's constantly switching or alternating. That means it doesn't go in every direction. It's just going in one of two directions, and it flips back and forth. DC battery, AC outlet. All right, I want you to make two columns in your notes, one for water current, one for electric current. The best way to think of electricity moving is kind of the same way that you think of water moving. Water always flows downhill. It goes from where it's highest to where it's lowest. Electricity flows from high electric potential to low electric potential. So, you think gravity is going from high potential energy to low potential energy. Electricity is going from high electrical potential energy to low electrical potential energy. So there's water going from high GPE to low GPE. Electricity goes from high voltage to low voltage. Electric potential is essentially voltage. It always goes high to low. And whenever there's a difference, you're going to have electricity moving or trying to move. You can, of course, use a pump to pump water all the way up to the top of that hill. So let's say you have a hill and water spilling down. The way you get it back up there, like, let's say a fountain, you're going to have a pump that will use to elevate the water to get a constant flow. A battery does the exact same thing. It pumps those electrons from a low electric potential energy at the bottom to pops them back up to the highest potential energy, and they flow again. And as they flow, they can do work. They can light up a light or turn a machine or something like that. But think of water and electricity very, very similar. Here you can see what we were just talking about. Battery kicks it up to high electrical potential energy, and as it falls, it does work going through that light bulb. Then it gets to low, and then kicks it back up. Same idea here. People are like the battery. They're carrying water up there, dumping it in there, and as it falls down, it does work. Maybe turning like a spinning wheel or something like that, but it's at lowest at the end, and a battery has to tip that energy back up to the top. So let's talk about Ohm's law, and we'll do some calculations on those in a minute. Voltage and resistance. Voltage is the energy per charge in a circuit, and we measure that in volts. Hey, one of the first ones where it actually makes sense. Resistance is the opposition to the flow. So if something doesn't want to flow through there, you would say it has a high resistance. The unit for this is the symbol there is the omega, and the unit is the ohm. All right, sorry, it's fine. Current is just that flow of electric charge. Think of it as like a water current. It's flowing there. And that is measured in amperes or amps, or sometimes we just write it as A. Conductor is something with a really small resistance, like a metal is a really good conductor. Electricity easily flows through there. The opposite of that would be an insulator, something with a really high resistance, like rubber. This is why if you're ever handling, electricity or something like that, you're going to have like rubber-coated tools that if you accidentally hit a live wire, there's a very, very high resistance there where hopefully the electricity won't jump into you and across your heart, causing a heart attack and all sorts of things. So some stuff you want very high resistance. This is why wires are wrapped in an insulator. You don't want the electricity jumping, making a shorter circuit than it's supposed to. Why does electricity shock people? Because it doesn't know how to conduct itself. All right, sorry. All right. Ohm's law states that the amount of current is proportional to the voltage and inversely proportional to the resistance, or we write this as V equals IR, where V is voltage, I is current. I know. That makes no sense. I apologize, but they ran out of C's and they had to move into something else. And then finally, R is resistance measured in ohms. So V, voltage, I, current, and R for resistance measured in ohms. And here you can see we have some practice problems on Ohm's law and the calculations with that.